graph is shown.
All right, so I guess I should just gonna kind of draw it roughly here.
I think it's a little below.
Oh, thank you. So let's see, it looks more like this. Oh, that's interesting. Okay. So part A says this is g of x. Part A says the limit as x approaches a.
Oh, okay, I have to read the directions. For the function g whose graph is shown, find a number a that satisfies the given description.
Okay, so this is kind of a mix and match kind of a thing. So g of x does not exist, but g of a is defined. This is a part of. So everywhere you see kind of a line, it's continuous, and g of x does exist. So it's got to be one of these points here. Here, here, here. Now here, the limit does not exist. That's good. But the point that, you know, with these little circles, it's not defined. Here, same thing, the limit, here the limit does exist, so forget that. So we're left with this. And here, the limit does not exist, right? Because as you come in from different directions, you get different values. But because they put a little round dot here, it does exist. So that's A. So that, what number is that? That's 4. X equals 4. Part B, okay, the limit does exist, but g of a is not defined. Okay, so once again, for all the smooth parts, the limit exists and it's defined, so that they don't count. Here, the limit doesn't exist, the limit doesn't exist. The limit exists here, but they haven't defined g of a. So that's this point, which is, I guess it's 5. C, they're just trying to exercise every possible weird thing that could happen. All right, so here, okay, now we're getting specific. The limit, and you have to look carefully, x approaches a from the left, from the left, yeah. Approaches a from the left, and limit x approaches a from the right. They exist, but the limit does not. Well, let's see. Here we have left and right limits, but it does exist. Here we have a left and a right limit, but the limit doesn't exist because it's not the same. So that point is 4. But also here, we have a left and right limit existing. But the limit again does not exist. So, set 2. Now that's distressing because they say find a number. Did I miss something in that problem? The limits both exist, but the limit that, yeah, I think both of these are fit that unless I missed something. Solve it. All right. So either one, I guess. And D says the limit x approaches a from the right equals g of x equals g of a. Okay, so here they want it where the limit from the right is equal to the value at the right, the limit coming from the left is not. Well, that's obviously this point. We come from the right, we get this point, and that point is how the function is defined. On the left, we get this point, but the function does not equal whatever this value is. So that's again, I guess x equals 4. You know, this is, to me, this is like, okay, do you know what a limit is? Do you know what these definitions are? In the real world, there's no problem like this. Even in the abstract mathematical world, there's no real problem like this. This is just trying to make sure you understand what these concepts are. Okay, are there other questions? Yes.
Number 53, on page 126.
Okay, I'm going to have to get, oh, I have one, 53. All right, give me a second while I, let's see, write names here. I saw something written in Fossey. Sorry, again, 126, number
53.
53. Okay, 53 says, number 53 on 126, f of x equals x squared plus n sine of x. Show that there is a number c such that f of c equals 1,000. Note they don't ask you to find c. This is that theorem we talked about. Sometimes when you have something like this, it helps to have a picture, just to kind of get you going on it. So x squared would be like this, and 10 sine x would be a sine function with amplitude 10. So this thing is kind of gonna, I mean, it's not that important, but it's kind of a upward parabola that kind of looks like that. Okay. And we want to find somewhere up here, 1,000, and we want to show that there has to be some c. Oh, well, that's easy. I mean, I'm sorry.
hard math class I ever took was in college. Well, actually, it was called linear algebra, but it wasn't. It was a lie. It was abstract algebra. It was modern abstract algebra. And the professor, who was a PhD, who was kind of fresh into the business, every time he'd see a problem, well, that's trivial. So, that's easy. So we have a theorem that says that if you have I'm not going to write it down exactly, but if you have a continuous function, f of x, and you have an f of a, which is some value a, and an f of value b, which is b, and you want to know if there exists an f of c, right? Well, because this is between these two, there has to be some c that this is true of. It's the intermediate value theorem. So all we really need to do to show this, we first have to establish this is continuous, right? So x squared we talked about is continuous. Sine of x we talked about is continuous. Product of a continuous function is continuous. And sum of two continuous functions is continuous. So we know this is continuous. There are no holes in this. So if we find two numbers, a and b, such that f of a is less than what we're looking for, 1,000, and f of b is greater than it, we're done. We've proved it. So the obvious choice here for a would be 0, because then f of a equals 0. Sky's the limit here. Let's say 1,000. Let's say 100. So f of x is 10,000 plus 10 sine of that 100. And we know sine is between 1 and -1. So this is at most plus or minus 10. So, this is greater, plus or minus something. And this is 0. So because 1,000's between them, we know that between 0 and 100 there has to be some c, where f of x is 1,000. We don't have a good algebraic way to find this, but we could use a numerical method. I guess in the future, when I want to do stuff on my calculator, I'll bring in equipment so everybody can see it clearly. But this is the kind of calculator I was talking about. And if I plug in, this is the y key. If I plug in that function, I should never do things ad hoc like this. They never work. All right, we'll try it anyway. Be brave. You have to be brave to get through math. Sine of x. And, they didn't say whether sine was radians or degrees. You can assume in this class, if it doesn't say degrees, it's radians. And I happen to know my calculator is probably in. Oh, it is in radians. Oh, good. All right, so I can graph this, and I get a nice little graph that just immediately goes off. So I'm going to zoom out. And, I guess what I could do is I could just say, I could put in another equation, y equals 1,000, and see where they intersect. There's a function to do that. Or I could be sneaky, I could just say minus 1,000, and then look for the 0. That would work too. Hey, if you don't have one of these, I can loan you one. I encourage you to start playing around with them because I don't really want you solving analytic problems with these. But it's really good for checking them, checking your answer, to make sure your answer makes sense. Right? Okay. Someone else? Miss anybody? I don't think so. Okay. Any other questions on homework?
One more. Page 93, number 29.
So it says determine the infinite limit. They're already telling you it's going to be infinite. There's really two possible answers. You know, you could kind of roll dice. It's either going to be infinity or negative infinity. So I guess that's what we're tasked with determining. And the function is limit as x approaches 5 from the right of x plus 1 over x minus 5. So I feel like this is the moment in the class where we all kind of meditate. Yes. Stop it. All right. Oh. When I was doing my graduate work at University of San Francisco, perfectly reasonable institution. At lunchtime, they like to play music in the quad. And then one lunch, I was in taking this exam for analysis. And the band they had was loud. I was sitting there going, and the professor, I looked at the professor and went like this. And his response was, all right, I guess we'll try and go forward. So there's a couple ways to address this. One way would be to, look at a graph for which, again, a calculator can be really nice. We can see that for x very large, these don't really matter. And so out here somewhere it's going to be 1. And for x both very, x very negative, it's going to also. So we know that. We might want to pick a point or two to give us some idea. So how about 0? 0 is negative 1/5. So that already gives us kind of a hint that it's going to do something like this. It's going to be asymptotic to 1. You can put it in your calculator. I see what it actually looks like. So now, wait a minute, did I miss something? Determine the infinite limit. Why is this an infinite? Oh, because at 5, oh, something's got to happen at 5. Right, that's 5. Okay, so what happens close to 5? Let's say we're a little bigger than 5. So this is a small positive number. This is just a 6, about 6. So here, it's got to go like that. Now, if we're a little below 5, we've got a kind of a negative number going to 0. So over here, it's got to go like this. Yeah, it's not continuous. It's got a break here. All right, so now we know what it looks like. So it just wants to know from the right what's happening. Oh, it goes to infinity. So it's not a, 99%, what are they asking, and 1% figuring it out. So, any other questions? Yes, George.
24, page 103.
I'll go over it. You got it figured out. 24. Evaluate the limit if it exists. If it exists. Let's get it started here. Limit as x approaches 2 minus x is the square root of x plus 2 minus 2. So see right away that the function is not continuous at 2. Because if you just plug in 2, you evaluate it as 2, you get what? 0 over 0. So while it may have a limit, it's not continuous. And look at this now. Encouraging. Not really cheating. It's just kind of getting around the point. You could plug this into a calculator and see what happens with 2. And I'll bet that you'll look at it and go, oh yeah, it's whatever we're going to find out. But we do want to know how to evaluate this analytically and just be really sure of what we've got. So we've done a few of these already. I hope you're getting the feeling. We're going to do some later in this class like this, where when you see something like this, you should have a knee-jerk reaction. You should think, wait a minute, a squared minus b squared equals a minus b. I guess I'm going to end up writing this a lot in class, now, aren't I? And you think, that's the pattern. What do I got here? I've got in the denominator, which is kind of part of the problem, I got something minus something. And if I could square this, I'd get rid of that square root sign, that would be good.
So I really want to multiply this by square root of x plus 2 plus 2. And of course, to make the world a nice place, I have to multiply it by 1 because I don't want to change it. So that's where I come up with this. Right? Now it's just a bunch of algebra. A squared, a plus b times a minus b times a plus b is a squared minus b squared. So that's going to be x plus 2 minus 4. And on top, I'm not even going to mess with it. X plus 2 plus 2. X plus 2 plus 2. Okay, so now, did that help any?
No, it's still 0.
2 minus x over x minus 2 times the square root of x plus 2 plus 2. This is still going to 0. But, so this, in fact, I want to rewrite this. I'm going to rewrite this as x minus 2 times negative 1. Oh, so now I can use my limit laws, which says that the limit of a product is the product of the limits. So I'm going to say the limit of x2 of whatever I started with, plus 2 minus 2, the limit x approaches 2 of, I'm going to put the minus over on here so it's really clear. Times negative, what am I left with? Square root of x plus 2 plus 2, and put the negative sign up. Limit x approaches 2. Okay, so what's the limit as x approaches 2, x minus 2 over x minus 2? It's 1. You can evaluate that. All right. This, no problem, it's a continuous function that you just plug into. So 4. There we have our answer 4. I encourage you in your free time, or you can sneak it in while I'm writing on the board. If you have a calculator, just try it. Plug this thing in and satisfy yourself that, you know, the calculator can help you check your work. All right. Yes?
Wouldn't it be negative 4?
Yeah. And that's another truffle I'm going to talk about someday. Yes. Thanks. Got the same thing?
No, I was just going to ask about another problem from the homework.
Okay.
Page 125, number 48.
Find the values of A and B that make F continuous everywhere. Okay. So what's our function? X squared minus bx plus 3 for x plus 3, 2x minus a plus b, x greater than or equal to. Okay, so our job is to set this up so A and B are such that
this is a continuous function. If we were to choose A and B randomly, presumably we would not get that. So, I'm sorry. Yeah, I'm. Would it help to close those windows for a few minutes? Open them when it stops? Or no?
It's gonna be a recurring event tonight.
You will persevere. The math is more important. Thank you all for being supportive. Yeah, okay. I mean, there's a lot of work here. With this guy, thank you. I got the first part of your name, Rumsey. Yeah, it's like, oh yeah, of course, x minus 2, x plus 2, or x minus 2. So the limit as you get to 2 of this thing is just going to be 4. So you want this guy, when he gets to 2, to be 4, right? I mean, this function isn't defined at 2, but he's just saying that's what the function is up to 2. And we know that the limit is, the limit is going to be 4. So we need A and B so that at 2, A and B reaches 4. So there's that. That's a little equation we can use. Ax squared minus b x plus 3, at 2. So a times 2 squared minus b times 2 plus 3 equals 4. Or 4a minus 2b equals 1. Okay, that's one equation in 2 unknowns. We can't solve that, but we have more information here. So what happens to this equation as it gets close to 3? Well, it becomes 9, I hate 9s and A's because mine look the same. Let's see. 9A minus 3B plus 3 equals, we don't know, do we? Oh.
6 minus A equals 6 minus A plus B.
Oh, giving away spoilers. Yeah, it has to equal, right, it has to equal what this equals at 3. Well, what does this equal at 3? This equals 6 minus A plus B. Is that what you meant? Yeah, thank you. Well, this is another equation in 2 unknowns. We have 2 equations and 2 unknowns. We ought to be able to make this work. Let's see. Bring the A over, that's 10A. Subtract B minus 4B equals, subtract 3. 4A minus 2B equals 1. And if I haven't made my usual at the board mistake, because I'm trying to do 3 things at once, 4 if you include, keeping that out of my head. Okay, so you should know how to do these, but I'm going to go through it just in case somebody
a little unsure. So the way I look here and say, I want to get rid of A or B, and it looks like 4B and 4B and 2B are pretty close. So I'm going to use elimination. I'm going to multiply this by -2. So I get -8A plus 4B, -2. Add them, and I get 2A equals 1, or A equals 1/2. And if I plug in 1/2 to either of these equations, I'll find B. That's how you solve it. I mean, you could look at this as, well, this is unfair. We're learning calculus. We have to remember, I mean, we have to be clever. We have to know about continuity. And we have to remember that algebra we learned 5 years ago. Yeah, it's sad, true. I'm not, this is good. It's good to exercise your brain this way and bring that stuff back. I'm not inclined to put things like this on exams because it just rattles people who are a little shaky, and it doesn't tell me if they learned the calculus. Given a couple hours, I'm sure anybody in this class, knowing, this strategy, could get the answers. So. Okay. Any last minute questions?
Can you do on the same page, number 75?
Oh, as soon as I make something on the board. Did you say page 75?
No, I think it's the same page.
104?
No, 126.
126?
126.
74?
75.
75. Oh, I always get asked this one. Do not expect anyone in the class to get this problem. Hope. This is a problem you have to do two things. You have to keep in mind what we learned, and you have to be very creative. And it's kind of a cool kind of thing because, well, wait. Why does the Tibetan monk, I'm going to read it in case you're not familiar. Tibetan monk leaves his monastery, I love this problem, at 7 a.m. and takes his usual path to the top of the mountain. He walks up, arriving at 7 p.m. So it takes 12 hours. The following morning, he starts at 7 a.m. at the top and takes the same path back, arriving at the monastery. They even tell you, use the intermediate value theorem, show that there is a point on the path that the monk will cross at exactly the same time of day on both days. How wonderful. They already messed up my day here with that urban cricket. There's a related problem in topology that, I don't know if you guys will get excited about. So you have your cup of tea, and you put in your spoon and you swirl it around. There's a theorem in topology that says that there's some point, in the fluid, it's traveling around, that at any moment has to be stationary. I think that point can move around, but at any moment there's one point it's not moving. Everything else is moving. This is kind of similar. It's like, oh, really? There has to be. All right. Oh,
Is that the Coriolis? Is that the Coriolis effect?
Coriolis effect has to do with the fact that
It's like
the Earth is turning,
No.
right? And
The eye or the center.
it's turning, and there's.
I'm not a,
Those are like the sustained winds and the sustained currents. Those are like the regular currents and the regular winds. That's
yeah,
like-
I mean, oh. Okay, I'm wrong, I'm thinking of the wrong thing. I think the Coriolis effect is kind of this one. Now, there's this myth that if you, you flush your toilet,
Oh, it goes the other way in the hemisphere?
that it'll start swirling around in one direction, but in Australia it goes the other way. It's half true. If you have, you know, some kind of fluid that's really, really calm, and you have like a little hole in it, you start dripping stuff out, eventually it's got to start spinning one direction or the other. And well, actually, in a perfect universe where you weren't moving at all, it wouldn't have to. All the, you know, fluid could just kind of drain like this. But because there's a slight little effect above, I guess it's above the equator or below the equator, because of the Earth, there's a little difference in the forces, and it'll start swirling around. And it, you know, if you do it right, you can show that the Earth is turning by doing this, but it's not a good way. There it is.
It's
Okay.
not flat.
Back to the Tibetan monk. Okay. So this is the bottom, this is the top. And so in the morning at 9, he kind of goes up the mountain. We'll call this, I don't know, we'll call this f of t, right? This is time and this is height. And then the next day, he kind of comes down. Again, starting at 9 a.m. and 9 p.m. And we'll call that g of t. Now, actually, you know, yes, this is a different day, but okay, who cares? We're going to start both of them, g and f at 0. And we're going to create a function d of t, which is f of t. I guess we should probably make it g of t, since it'll be positive, minus f of t. All right. So at 9 a.m., I guess we'll call the height of the mountain m. At d of t, g minus t at t of 0, I guess 9 a.m. This is m, right? We start, you know, a different way to think of it is imagine there are two monks, right? And they're both starting on the same day. Oh, that makes it really simple, doesn't it?
It's just 3 p.m.
Right, they're just they have to meet somewhere. I mean, you can't jump over each other. But they asked you to use the intermediate value theorem. So d of 9 p.m., that's over here. That's negative m, right? G is 0 and f is m. Well, we know there has to be some c where this is 0. The distance between them is 0. And there's only one path, so they have to be at the same location. So that's it's just a fun little problem. You know, if you agonized over it and just went to bed thinking, I'm a failure, I'm sorry, you're not. It's a really hard problem. You have to be very creative and persistent. Or you can Google it. If you Google it, you probably found the Tibetan monk, you know, whatever problem, you could find it that way. which would be cheating, but, you know. All right, are we done with homework problem?
Can you do 56,
56.
page 126?
Do you mind if I take a picture before you erase it?
I don't. I'll start over here. So, page 126, number 56. Use the intermediate value theorem to show that there's a solution of the given equation in the specified interval. So this is len of x equals x minus square root of x in the interval 2, 3. So, all right. I think we're going to use exactly the same strategy here. We're going to create a function, call it f of x, and it's equal to negative log of x plus x minus square root of x. The point being that where this is 0, we found our solution. They're not asking for what the solution is, they just want to know that there is one. And we want to use the intermediate value theorem to prove this. So we're going to use the intermediate value theorem to show that between 2 and 3, this state must exist. There must be some value. So how do we do it? Well, okay, that's f of 2. Well, it's negative log of 2 plus 2 minus square root of 2. Now a calculator might help if you're not real sure about this. But, we got 2. Square root of 2 is about 1.4, so that's 0.6. And the log of 2, it's the log of 2. Well, log of, I just use my calculator. So, the natural log of 2, it's about 0.693. All right. So minus 0.693. I don't really even care. It's negative. I don't know what it is. Doesn't even matter. We'll just estimate. Okay, it's negative. All right. So now let's try 3. Negative log of 3 plus 2. Plus 3 minus square root of 3. Well, I happen to know square root of 3 is about 1.7. 1.7, 2, 1.2. Oh, natural log of 3 is definitely going to be, it's going to be a little bigger than 1. We'll have to find out. Okay. So natural log of 3 is 1.09. So this is 0.11. Well, that's what we needed. This is positive, this is negative. So between 2 and 3, somewhere this is equal to 0. And where it's equal to 0, we have a solution to this. That's how you use the intermediate value theorem in this case. And it's a little tricky, a little different from probably what you kind of questions you've seen in algebra or pre-calc. All right. I'm fine spending a lot of time on the homework if that's what people need. I think we're just about at break time. So why don't we go ahead, take a break for a couple minutes, and see if we can cover what I wanted to cover today.
Yeah, please.
So your attention, please. This is section. We covered this a little bit. We're going to pick up. We were talking about
limits at infinity. We want to just summarize. We have limits where you have some limit at some finite value, which has some finite value. We have limits, some finite value that really don't exist, but they could be limits at infinity or negative infinity. Function just grows or dies. And now we're talking about limits as x goes to infinity or negative infinity. We're talking about ones that have a finite value, and we're also going to talk briefly about functions where at infinity they go off to infinity. Keep in mind, again, infinity is not a number, it's just kind of a direction. We briefly took a look at function x squared minus 1 over x squared plus 1, which has this graph that is asymptotic to y equals 1. That's an example where the limit as you go in the positive direction is 1, in the negative direction is also 1. That's an example of this. I think we were just getting to, we were going to look at the limit of the arctan function as x goes to infinity. And if you think about the tangent function, it kind of has these vertical asymptotes, and then it's periodic, so it repeats. But for the arctan function, we have to limit the domain here so that we get a function, not just a relation. So the arctan function kind of looks like this. Just kind of flip this over the y equals x-axis. And again, it's asymptotic to this pi over 2, and down here, negative pi over 2. So again, we would say the limit as the arctan of x goes to infinity is pi over 2. And same thing as x goes to negative infinity, arctan. X is going to go to negative pi over 2. And you're typically, when this happens, you're going to have a horizontal asymptote. All right, so let's look at some other really, I hope, easy kind of limits. Think of the limit as x approaches 0, 1 over x. Well, if you pick some small, I mean, this is never 0. If you pick some small, what do we say, epsilon, like I want to get 1 over x within, we pick some number, 10 to the minus 1,000 of 0. You can choose an x that will cause that to happen. No matter how small you want, how close you want to get, you can get there. So the limit here is 0. Likewise, 1 over x to n, as long as n is greater than 0. This again, this is going to go to 0 even more quickly.
Now here's like a typical problem you might see on this issue in
The homework. What is the limit as x goes to infinity of 3x squared minus 2? I think we just throw in these terms to make it look complicated when it's really not. Plus 4x plus 1.
Well, I'm going to show you kind of the direct, clear way to do it, but if you think about this, as x gets big, these terms are going to become insignificant compared to x squared. And x squared over x squared is going to go to 1, so this is probably going to go to 3/5. But we'd like a little nicer way to see that. So what we can do is we can multiply this by 1 over x squared over 1 over x squared. No point using my hand as an eraser, is there? And what do we get? We get 3x squared minus x minus 2 over x squared, and 5x squared plus 4x plus 1 over x squared, which now we're going to rewrite this as, oh, this is going to be 3 minus 1 over x minus 2 over x squared, and this will be 5 plus 4 over x plus 1 over x squared. Now, we're looking at this and we're thinking about the limit as x goes to infinity, and we're also thinking about our limit laws, right? Let's just look at the top for a second. 3 minus 1 over x. Well, 1 over x we saw goes to 0. Also, 1 over x squared is going to go to 0. So this is just 3. And in the same way, the denominator, 4 over x and 1 over x squared are going to go to 0, so this is just going to be 5. And, again, it's a little trickier to do this on a calculator, because you have to start looking out to the side. But you'll see that you're going to get a function that, I don't know if it's going to come from the top or the bottom, but, here's 3/5, and you're going to see that the function approaches 3/5 asymptotically. Let's do another similar problem, but a little different. You might see something like on homework. How about the limit as x approaches infinity, square root of 2x squared plus 1 over 3x minus 5. Well, even though there's an x squared here, a square root here, this same strategy is going to work. We're going to multiply this by 1 over x over 1 over x. Do the denominator first. That's easy. That's just going to be 3 minus 5 over x. So you can see the denominator is going to go to 3. But now to put this x under the square root, we have to square it, right? So it's going to be square root of 2x squared plus 1 over x squared. So square root of 2 plus 1 over x squared over 3 minus 5 over x. And as we take the limit, as x gets very large, these disappear. And so this is going to approach square root of 2 over 3. So that's how you would typically evaluate these. Is it negative? Or a negative I missed?
Your book has like a negative square root, 2 over 3.
Yeah.
I'm not sure what the question is.
This book just has a negative square
Yeah.
root of 2 over 3.
For this problem?
2x squared plus 1 over 3x minus 5. When n is x approaches infinity. Example 4.
That's for negative.
Oh, yeah.
It's negative.
No, it shows regular.
If you like, we'll make this negative infinity. And then what do we get here? This goes to negative.
How does that change?
So there's like that blank space in the center.
Well, this is positive and this is negative. I can see that. Oh, well. That's funny. Over here I can see it's going to go to negative square root of 2 over 3. But over here I'm not so sure. Maybe I've made some calculation error. Huh. Well, I'll have to go investigate that. But the problem I did correctly. I just did a different problem in the book. Is that fair enough? Fair in the moment? Maybe I didn't like something. All right. Where does that minus sign go?
I think it's like the same problem that we just run, both infinity and negative infinity.
Yeah, I get that, and it kind of feels to me like, oh, well, yeah, I can see where, yeah. All right, let's, I don't see what I'm doing wrong in this case, that it comes out wrong. I would like to know what's crossing out. So this gets very big negatively. It gets squared here, so this stays positive. This becomes negative. So why, when I do this, does this not come out negative? Okay, I don't want to spend the whole class figuring out my stupid mistake. I will come back with an answer, right? Is that fair? We have something much more ugly to deal with here, so. Did you figure out where I went wrong?
I think it's, they have like two separate things on the same graph. They have like an infinity and a negative infinity.
Well, it's the same function, it's just, they're looking at it in the other direction. And it's obvious to me that this here is positive and this is negative. So it's going to be negative, whatever it is. But why is my algebra here not showing me that? It should.
You did like the same thing as the book in the first part. They do something weird in like the second.
All right, well, I'll come back. I'll come back on Thursday and have this worked out.
I'm sure I'll just figure it out.
Okay. All right. I have I have a hard problem, well, I think it's hard. Limit as x goes to infinity of square root of x squared plus 1 minus x. Now, it'd be nice if it was just kind of obvious what's happening, but you can see x squared plus 1, the square root of it. As x gets very large, this is going to approach x. And I'm subtracting x. So maybe it goes to 0? Maybe? I'm not sure. I want to write this in some way where it's more transparent. So, once again, you notice we've got square root of something minus something, and we think a squared minus b squared, So let's multiply the top here by square root of x squared plus 1 plus x, and just make sure we don't mess things up. We'll multiply the denominator also. Okay? So what does this become? Well, a minus b becomes a plus b, a squared minus b squared, x squared plus 1 minus x squared. And on the denominator, we have x squared plus 1 plus x. So this becomes 1 over square root of x squared plus 1 plus x. Well, now it's pretty obvious. I mean, this is going towards x, this is going towards x over 1. But as x goes to infinity, obviously this is going to go to 0. All right, so that covers these guys. And we're just going to take a look at one example of this. A limit at infinity that goes to infinity. And the example is really simple. We pick some exponential function. And limit as x approaches infinity. I want a positive greater than 1. This goes to infinity. Again, keep in mind, this is not a number, it's just an indication. We can get larger and larger beyond any number we pick. I thought that was all I had to say about it, but oh, there's one example they want me to do. I'm fine with that. Consider, this might be a homework problem, x going to infinity of x squared plus x over 3 minus x. And we're going to use the same strategy we used before. We're just going to multiply this by 1 over x over 1 over x. So what do we get? We get x plus 1 over 3 over x minus 1. Well, this is going to grow without bound. And this is going to become -1. So this is going to go to negative infinity. So please move forward. All right. Yes.
Why do you keep multiplying by 1 over x? I understand that's like the foundation of this. section.
Well, okay, I'm multiplying by 1 over x over 1 over x, which is a form of 1. So I'm not changing what I have. But when I'm done, I can look at this and I can evaluate it, you know, as I get close to my limit. I can see right here that 3 over x, as x gets really large, goes to 0. So I'm left with minus 1. Here, in this case, I have an x, it's going to infinity, and that's how I come up with this.
Okay.
Is that okay?
Yeah, I still don't understand the significance of 1 over x, though. I missed
The
that.
significance of it,
Yeah, 'cause you're multiplying
it's
by-
an algebraic trick
Right.
to help us. Just as back here, you know, when I multiplied by a plus b, right? And a minus b, and I multiplied by a plus b over a. What did I multiply? A plus b over a plus b. I did it to put it in a form that I could inspect it and look at and see where the limit is going.
I'm looking at the theorem though, where it says the limit as x approaches infinity of 1 over x equals 0. So it looks like you're taking it from the theorem there. I'm just wondering.
Well, here I certainly am. Yes. I'm hand waving a little, but yes. I can say this goes to 0 because I know 1 over x goes to 0.
So it's the fact that it goes to 0, which makes it useful. It makes things go to 0.
It's the limit. Yeah, in the limit, it becomes 0.
Why 1 over x over 1 over x and not 1 over x squared over 1 over x squared?
Well, when you're doing things, you try them and you see if they help. So I already know where I'm going, so it looks like I'm not a genius. That's, perfectly reasonable. Let's see what happens when we do that. Maybe it'll be useful, maybe it's a dead end, we'll find out. So this is 1 plus 1 over x. And this is 3 over x squared minus 1 over x. Okay. So now we want to look at this and say, well, what happens as x gets very large? Well, we can tell very easily here this is going to 1. Not as obvious. 3 over x squared minus 1 over x as x gets very large. Let's put it over a common denominator. 3x minus 1. Wait. I did that wrong. 3 minus x over x squared. Does that help any? Again, I'm trying to figure out what happens if x gets very, I could look at this and I can say, well, obviously x squared is going to get bigger much faster than negative x. What's not clear to me, well, I guess x is going to get much bigger than 3. So I'm going to end up, this is going to tend towards negative x over x squared, which is like 1 over x, which is minus 0, right?
Wait, I have a suggestion. Can't you plug in infinity?
Okay, so the reason we try and avoid up here, in your desk, you kind of see, I can plug in infinity and that works, yes. The reason I have to avoid that up here is infinity is not a number. I can't plug it in, really. I can see what happens. I can understand what it means. I can't, I may say I can't plug infinity in here, but I can say what happens to this as x gets very large. It goes to 0, but it's always negative.
So wouldn't it be infinity over negative infinity? Thus making it negative infinity?
It's 1 over.
No, if you were to plug it in.
I'm gonna go with, just gonna,
No, just try it.
you mean here or
Yeah.
here?
And no, up there.
Up there.
Yeah.
So what you're saying is like, do this. Right?
Yeah, try it.
And now what do I do? I guess I can erase this because it's irrelevant.
Yeah, it'll be negative.
I can erase this because it's irrelevant. Now I get negative infinity. Okay.
Yeah.
As a kind of intuitive strategy, be my guest. But be careful, because we're going to get into situations like this, where you have what do we do with that? How did we get there, right? Well, wait a minute. Wait. Well, if I got there like this, then all right, I know it's that. If I got there like this, then oh wait a minute, it's going to be negative infinity, and as we will see later in the class, there are circumstances where this will be a number. So this will, you'll have a limit, you'll have the difference between two things that are getting very, very large, but they will coalesce on some number. They'll get very close to some number. So you want to be careful about that. I understand, you know, I've done this myself. I went, oh, you just look, just, you know, plug in. It's not a number. You got to be careful. You just have to keep that in mind.
Okay.
Sometimes it will work. So it's not
Like
a,
in that case.
it's not a bad shortcut if you know what you're doing and you're careful about it.
But in that case, I can do that, right?
Well, you can, I can't. I would be fired.
Oh.
You know, there are rules.
Yeah.
You can date your classmates. I can't. It's just one of the rules, right? I hope I don't get fired for saying that. Someone's saying he wants. And we're saying I'm on tape, so taking you right to court. All right. Okay, so we're at that wonderful moment where we can get down to brass tacks here. Derivatives. And the book likes to add rate of change. And this is section 2.7 in the book. So we're going to spend a lot of time over the next few classes learning about what a derivative is, how to find one, math. And, you know, when I kind of get to the point of what a derivative is, you can go, really? All that effort? I mean, that's what this whole class is about? And so before I go into this, I want to talk a little bit about why this is important and how it, you know, might affect your lives or your education. So, first thing I'm going to do, I'm going to describe a situation many of you have experienced. You're driving down a highway. I like to think of, California. There's this highway, I-5. Kind of run over there and you end up in LA. It's just kind of straight. You get out there in the car. The limit is 70. You go 70, they're all passing you, you're going 80. It's kind of boring. If you really wanted scenery, you'd go down 101 or even better, Route 1. If you're from out of the state and you have a vacation out of the country, go down Route 1, nice and slow. But
It's
you're
on the
going,
west. It's been closed though. When you get down like towards LA, there's been like construction. You have to take like a whole crazy like thing. I don't want to buy it anyway.
oh, okay. Last, up to the minute traffic report, yes, that's right. I don't know. I've been here for 40 years. I don't keep up. All right, so you're driving and you're kind of bored, and you don't have a passenger or a radio, and so you're kind of like, oh, how long is this going to take? And you look at what information you do have. You've got a clock, keeps the time. You've got an odometer. Clock is kind of T, the odometer is kind of X. And you've got a speedometer. V, velocity. Or like your physics major is S, speed. Because velocity is something a little different. And you travel along, and you notice after about 10 minutes that you've gone 15 miles. And this is a sixth of an hour. You divide 6 into 15, a sixth into 15. So that's, you're going 80 miles per hour. Average. Right? Average. But you look at your speedometer and it's, right, kind of wiggling around. I mean, maybe you've got cruise control, so it's a little better, but when you go up the hills, it slows down a little. So, you start to take points down. You graph the speedometer. Maybe you've got a computer in there now. We have lots of computers in cars. And your graph kind of looks like this. This is T, and this is X, your odometer. Kind of looks like this. So, we think about what we calculated here as if we had a constant velocity. That's our average velocity. It kind of looks like that, but on the graph, we get these bumps. We think, well, what is the speedometer actually measuring here? Well, if we had cruise control and it was nice and straight, it would be obvious. It's just the slope here. But at any particular point, we just look at 2 points real close together. We can form a straight line. We have a little bump. We can find a tangent, which has a slope, right? We slow down. I don't think it was that slow. But this is kind of what a derivative is about. It's like we want to know at each point what the velocity was. Now, you could take data points, if you're a scientist, and you can approximate that function. You can get the average, anybody can get the average. But getting the, what we call the instantaneous velocity, the velocity is just at one point in time, that's what we want to do in calculus a lot. And again, these are valuable for different things. You know, the average velocity is going to tell you how long it's going to take you to get to LA. You know, hours and hours. But the instantaneous velocity is going to tell you if you're likely to get a speeding ticket, right? So it's kind of slightly different information. So the process of finding all these individual velocities and maybe graphing them, is what we're going to call differentiation, or if you think of x, this is t, I'll call it f of x. Call it d of x, it's a distance, right? We're going to find the derivative of this function. Now, if all you could do with this is kind of figure out stuff about driving to LA or driving around the city, it wouldn't be that useful. But really what we're doing here is we're looking at a rate of change. And most of you are going to be involved in a major where rates of change will come up. So here's some other examples you might want to consider. In medicine, you know, you give a drug some. You're welcome to laugh at my awful stick figures here. Some patient, you know, right? He's probably not happy. He's probably sick. And you want to know how much drug is in that person's body over time. Well, he's going to take it into his gut. He's going to absorb it at a certain rate. And he's also going to eliminate it at a certain rate. So in medicine, and actually in biology, this is, you know, rates of change are very important. You're going to be an economist. And I'm simplifying here beyond stupidity, but, you know, got a bank. The bank is Chase. And you put money in the bank. And then people borrow money from the bank. And there's a rate at which money moves through the bank. And if you've taken Economics 101, you know that that rate actually is something that the federal government has some control over. They control something called the reserve rate. How much money does Chase have to hold on to? They can't loan it all, can they? Right. So in economics, you're going to need to know this. In physics, this is ridiculous. I'm just going to give you one silly example. All over physics, just all these different rates. You know, electromagnetic fields and everything. But my example is just fluid mechanics, where you've got a pipe and you've got fluid going in, and you change the size of the pipe or, you know, the type of fluid, you know, friction, rate of changes are just all over the place. And finally, my favorite, because I was an astrophysics major. If you're studying a star, like, we'll just call this the sun, there's energy that gets created in the core, in the center, in nuclear reactions. And this energy is traveling out through this big gaseous sphere. And it has various transport mechanisms. Some of it's just, you know, like photons, energy, some of its convection. If you remember convection, it's like blobs of gas move out. And there's some conduction, the atoms bouncing around. And, you know, if you take a course in stellar structure, you're just using all these equations with rates of change. So that's why we're studying calculus. I'm sure I didn't mention everybody's major, but you know, there's a reason for all this. All right. I'm gonna run out of time, I'm sure, before I'm happy. But that's all right. Okay, so let's get down to the meat of this. So, you know, of course, from algebra, that if we have a line, we have a slope, which we usually call m, you might say delta y over delta x, or if we take 2 points, y2 minus y1 over x2 minus x1. I hope you're all familiar with that. So, if we take some function, which I'm going to conveniently draw for my own purposes, and we take 2 points on it. I'm going to call this A. I'm going to call this X. So this is f of A, and this is f of X. The idea here is I'm kind of anchoring A, but X I can kind of move around if I want. And I want to approximate the slope between these 2 points. I could draw a straight line through them. And then my approximate derivative at that point at A would be f of x minus f of A over x minus A. And this is just my y2 minus y1 minus x1. Now, if I was to try and move this x closer and closer and closer, eventually x minus A would go to 0. And I can't evaluate it. What I can do, can say that my slope at that point, there's a notation we often use this, we'll talk about this at some point, but there's it's not a quote mark. What is this? Thank you. You know everything about math, but I'm forgetting everything else in the world. You can treat this as a limit as x approaches A of f of x minus f of A, x minus A. I'm going to say one more thing about this before we're done. This by itself is not as useful as a version that we create by using a variable h, which we use kind of the same way we use epsilon. Just some value that's going to get very small. So h equals x minus a. So we're going to rewrite this as the derivative at x is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. And you might want to write this down. We'll we'll pick up here on Thursday. This is our definition of the limit of the